Okay, so this is the last video in this section of videos about images and pixels. And what I want to talk about in this video is computer vision. Creating, using an image as something other than a thing we draw on the screen or a thing we look up colors from to draw other things on the screen. What does it mean to try to have our program, our thing we're making and processing, see the world in some capacity? Maybe to determine if there's a user present, maybe to determine if the user is waving his or her hand, maybe to determine what color clothes the user is wearing. There are lots of things we might be able to figure out from a scene if we have a camera looking at that scene or an image that was taken from somewhere. Okay, so this is a huge topic, and somebody who actually knows what they're talking about could probably make a long series of videos going quite in depth about topics and examples in computer vision. What I'm going to do in this short 10 to 20 minutes here is simply kind of look at some of the basics. What are some of the key fundamental pieces that we need to know about or figure out in order to build our own computer vision application? And then what are some pathways to doing more stuff with that? So let's kind of like start with a basic kind of classic scenario. Let's say we have a scene. There is a camera from our computer pointed into a room, and in that room there is a very bright light. As this sort of weird looking light bulb thing that I drew here, and maybe there is a person, like, I can't draw at all, holding onto that light bulb and they're moving it around. Could we have a camera over here looking at this scene, track that light bulb? How would we do that? Well, conceptually we might say, aha, let's find the brightest pixel in this image. How could we find the brightest pixel in this image? Well, we might start with this pixel and see that this pixel is very dark. It's has a brightness value of 0, and then we look at the next one and see it has a brightness value of 0, and the next one has a brightness value of 3, and the next one has a brightness value of 4, and then 0 again, and eventually we might get around and be like, oh look, there's a pixel over here with a brightness value of 255. That's really bright. Let's remember where this XY location is, and as we get to the end of looking at all the pixels, which one had the highest, brightest value. This is searching through the pixels to try to see where the brightest pixel is. So let's look at a kind of variation on this for a second. Over here I have an example which I'm going to run for you that's hopefully going to pull up an image. I have a camera right here looking at me. And you can see there I am above over here, and I'm going to take this blue marker and I'm going to click on it, and you can see, oh, I'm kind of drawing a dot following this blue marker. I'm tracking the blue color in this image that's coming from a camera. How is this done? Now, you can see there's a lot of problems there. It wasn't so perfectly accurate, and there's a lot of issues here that I want to take a minute to discuss too. But let's just say, for the sake of argument, that is the be-all, end-all of computer vision. How do we write a program that does that? That recognizes a color in an image and continuously follows that color as it moves over time. Very similar to what we talked about here. The difference is maybe we're looking for the pixel that's the most blue, not the pixel that's the most bright. So one key thing we need to figure out here is how do we determine if a color is similar to another color? So let's think about these two colors here. 0, 100, 255, R, G, B. And now let's take another, this is some color, it's kind of bluish greenish. Now let's take another color, 250, 255. So how similar are these colors? Well, one thing we could say is like, the red values are 200 units apart, the green values are 50 units apart, and the blue values are 0 units apart. So I could kind of give it a similarity score of 250, where 0 would be the most similar, right, if all of these values were equal, and 255 times 3 would be the largest difference if all of these, values were only 0 or 255. So we can see here, like taking the difference, subtracting one color from another, and you'll notice I'm using the absolute value, meaning 200 minus 0 is 200, 50 minus 100 is actually negative 50, but I don't care whether this one's greater or this one's greater. I just want to know how far apart are they. So this is kind of a way conceptually that we can see how different are these colors. It turns out that an accurate way that we can get this all into one line of code, let's say I have these two colors as in variables R1, G1, B1, and R2, G2, B2, I can say float the difference between two colors is the distance between those colors. R1, G1, B1, and R2, G2, B2. This line of code right here, using processing's distance function, will actually give me a rating, a value, a numeric value that indicates how similar these two colors are. How does that work? Well, distance probably makes sense to you. If I have a three-dimensional space, which is where I am right now, my hands are a certain distance apart. Now they're getting closer and closer and closer. Well, there's three-dimensional space. There's like an x-axis, a y-axis, and a z-axis. And things in this room that are closer to each other have a lower distance. Well, we could think of these axes, instead of being x, y, and z, as being the red axis, the green axis, the blue axis. What if we filled this three-dimensional space with every possible color? Colors that are nearer to each other would be more similar than colors that are further apart from each other. And this use of Euclidean distance, the distance formula, even though conceptually we think of it as something that has to do with physical space, or even two-dimensional space in the case of two-dimensional distance, we can use that with color as well. Now, why am I spending all this time talking about just this distance formula? This is what we need to do. If we're trying to find the color that is the most blue, what if I look at this pixel and find its distance from blue? Then the next pixel and find its distance from blue. Then the next pixel and find its distance to blue. One of those pixels will hold the world record for smallest distance to blue. And if I keep track of that record, does this pixel break the record? No, throw it away. Does this pixel break the record? No, throw it away. Does this pixel break the record? Yes, it does. Keep its XY. Now keep going. And if I ever find anything else that's greater than that, then keep those XY. After I finish looping through all the pixels, I'm going to find the XY location of the pixel that is most blue. So the two things that we need are the things we already have is we know how to loop through all the pixels. The things that we don't have necessarily from before is how to find the similarity between two pixels. This distance function is a great way of doing it. And also how to keep track of which pixel is the one I want to remember later after I finish looping through everything. So let's go back and look at this example again. And I need to run it. So there's a few things I guess I'll point out in the code. But let's just make this example run again. I'm going to hold up this blue marker. I'm going to click on it. You can see, it's tracking it. It's continually finding this blue marker. Now, a couple things that are going to fail here. Let's see if I want to track the green. I'm clicking on it and, this whole background is green. So tracking something green isn't going to do very good. What if I click on my nose to try to track the color of my nose? The color of my nose is similar to my forehead, is similar to my hands. So there's a lot of flaws in this scenario of just looking for a single pixel. Notice how much this is jumping around. We could add a little easing or interpolation that might help that. There's a lot of flaws in this. And honestly, if we really want to track a color, an object that has a specific color in a image, it probably makes more sense to look for an area of pixels that are very similar. And we're just looking for a single pixel. So but this, while this might not be the most useful application in a kind of real interactive scenario, this demonstrates a lot of the basic principles of computer vision. So let's look at a couple things. One is, in the code here, one thing I want to point out is this is exactly what I'm talking about. We have a current color from the video, and I need to get its red, green, and blue values. And then I have a color that I'm tracking. That's the color I'm searching for. So I want to know what's the distance between the current pixel I'm looking at and the color that I'm tracking. So here's the distance function being used inside of this nested pixel loop. The other thing that I'll point out is we're starting, before we go through the loop, we keep track of what's the world record. The world record is some big number that's obviously the first pixel is going to beat. And then we need to keep track of that X and Y point. So at any moment, if we find a pixel with a distance that's less than the world record, then the new world record is that pixel, and that X and Y we should save. So this is that second piece. The first piece of something new here is that we need to figure out how are two colors different or similar using the distance function. And another piece is how do we, while we're looping through, how do we keep track of which is our favorite pixel essentially? Is this our new favorite? It is. Save it. And we'll save it again if we find. So it doesn't actually matter what order we look through the pixels. We're going to hold on to that quote-unquote best pixel all the way through that loop. Okay, so this is giving you some of the basics. Again, you can see there's a lot of flaws here. If I were to give you an exercise, I might try to add some easing so that, let's look at, so even if I'm, oh, this is a black pen. Let's go back to the blue. So even if it's, we could probably get this to be at least somewhat smooth. The other thing I should point out here is there's no need to display the video. Look at this. Ooh, I'm magically controlling the circle above me. So one thing to recognize here is the camera is really acting as a sensor. There's nothing about it that we're using for display purposes. We're just reading the image and getting some, kind of analyzing it for some piece of information. So just recently at the winter show here at ITP, students built a spray, an interactive paint application where you would hold a spray can up to the wall, and inside of that spray can was a very bright green LED, and there was a camera on the wall. So the camera was able to track where that spray can was simply by tracking a very bright LED. So there's a lot of cases where you might want to track something, find it simply with color. I should point out that another, I'm going to just jump to this. Another scenario where you might like to look at the difference between pixels is for looking for motion. So I'm going to stand here and try to stand very, very still. And you can see when I stand very, very still, except for my mouth moving, you're not seeing any black pixels. But if I move around a lot, you're seeing a lot of black pixels. So one thing that you can do is you can find motion by saying, I have one frame of video and I have the next frame of video. Let me compare each pixel. A pixel that changes is likely where there's motion, right? Because if my hand is never moving, the pixel color here is not changing. But as soon as I move my hand, the pixel colors are changing. Now notice that even just with subtle movements, we're getting, in a way, we're finding the edges of my hand. Because if you think about it, the pixel, even as I move my hand, the pixel colors in the center of my hand aren't really changing. It's only changing along the edge where this white part, where this part of my skin meets the green part of this green screen that you can't see because you see a computer screen. So this is another scenario, and all these examples are in the Learning Processing GitHub repository, which I'll connect. This one is example 16.13. So this is a little bit about computer vision here. I guess I'll just show you one more here. There's another example which we can look at just how many pixels have changed per frame. So if very few pixels have changed per frame, you see this small dot in the center. And as I move around a lot of pixels are changing. The dot is getting bigger. So this is a scenario where we can use, and maybe an exercise might be, could you find where the motion is? So you could create an application where as I'm waving my hand, something's able to follow the thing that is moving. So there's a lot of possibilities here in how you use what the computer can see. Can you find the edges? We looked at edge detection in image processing, finding a specific color, finding the brightest pixel, finding the darkest pixel, finding pixels that are moving. These are the types of things you can do writing your own code in processing. However, this is not a new idea. I didn't invent any of this. In fact, I know very little about this compared to a lot of people in this world. And in fact, if you want to work on a computer vision application, it's quite likely that, am I recording? Yes. And how long? Oh, 13 minutes, we're fine. So it's quite likely that what you want to end up doing is using a library that has a lot of computer vision functionality built into it. So one library that I would recommend you look at is, I'm going to have to just sort of Google search this here really quickly, GitHub, is OpenCV for processing. So this is a library by Greg Borenstein. OpenCV is an open source computer vision library originally developed by Intel, now maintained by open source collectives. This is me. And you can see here that there's a lot of functionality. It can find your face. It can do all sorts of image processing. It can look for blobs and contours. So a lot of the stuff that we might spend hours or weeks or days or months trying to program from scratch are features that are built into a library. And you can even see as I get down here, there's lots of kind of really interesting features like I don't know, recognizing a card, for example. Okay, so, recognizing different markers in an image. So anyway, okay, so well, let me show you one thing that this is kind of classically used for is for face detection. So let me run this one. Let me close these out. And back to processing and run this. So one of the things that OpenCV will do for you is it will find faces in an image. So you can see here, as soon as I turn to the side, by the way, it's not recognizing my profile, only if I'm looking dead on. So what OpenCV will do for you is it will give you a rectangle. Now this is quite different than face recognition, right? This is just face detection. Oh, there's a face. There it is. That's how big it is. But you could imagine some applications you might do here is how many people are there? Is somebody looking straight versus looking to the side? There was a project just here in the ITP Winter Show where two people are standing in scene and their faces are swapped. So there's a lot of creative possibilities here. You know, if you use Google Hangout, you can see that you can add. There's all these features. We can add a hat or a mustache on somebody. You could do this with the OpenCV library as well. So this is something that I might encourage you to take a look into as a possibility. And one thing that OpenCV has also is blob detection. So finding areas of brightness or areas of darkness, which is very useful in a tracking sense as well. So the last piece that I want to just kind of demo for you here, and I'm going to have to plug it in, is that there is a thing called the Microsoft Kinect. I'm afraid to pick this up. Can you see this? This is the Microsoft Kinect. This thing has a camera in it, a regular RGB camera. It has an infrared camera and it has an infrared projector. So what this sensor is going to do, this camera, this depth sensor, and let me see if I can open this example up. And oops, hello. This is what happened. Oh, there we go. Okay. So you can see that this is showing us a couple different things. One is, here's another image of me in this room. You can see that I have a little TV over here where I can watch myself. This is all very strange. And there's just a camera coming out of this Kinect. But then there's also this image over here. This image is a depth map. Now, the way that the screen captures work, it's very hard to see what's going on here. But you can see that my hand is a little bit brighter, and now it's quite a bit darker. And you can see as I put it in here, we can't see it anymore. So what the Microsoft Kinect, and this is the old Kinect, this is the original model from a few years ago, 1414 is the model number. What it does is it's able to not just say, like, here's a pixel, and here's its red, green, and blue value. What it says is, here's a pixel, and here's how far it is from the Kinect, from the camera, from the sensor, in millimeters. So you can know what's close, what's far away. And another way of looking at this, I think, sorry, I had a technical malfunction. So what you can see here in this scenario is that I'm drawing each pixel as a point in three-dimensional space. And it's a little hard to see probably where we are. Based on this orientation, I'm looking at 12 different places. But you can see that this is essentially the data visualized in 3 dimensions. So some really basic 3D scanning of terms of a scene. What I'm not using here is there's a library called OpenNI, simple OpenNI, which is actually now, OpenNI was purchased by Apple. Okay, here's the thing. I don't want to ramble for the next 20 minutes about all the different versions of Kinects and which ones work with which operating system and which library. But what you have right now at this very moment, there's the original Kinect that came out a few years ago that you can use. There's a library for PC and processing that you can use. There's 2 libraries for the Mac and processing. One, which is OpenConnect, which is a library that I built on top of some open source drivers for the Kinect, and there's also something called Simple OpenNI, which uses OpenNI, which has since been purchased by Apple and has been shut down. So while all of this works, if you're interested in the Kinect, you probably want to go and look for Kinect version 2. That's the newer Kinect. It's a bit higher resolution. A lot of the skeleton tracking, which I haven't really mentioned yet, is a bit more accurate, I think. However, there aren't open source drivers as easily available for the new Kinect. And so there is an official Microsoft developers kit, and you can use that with processing. However, it's only for Windows. And at the moment, there are a lot of people here at ITP and probably other places in the world working on ways to pass the information from the Kinect and a PC over the network. What you have to realize is the Kinect itself is just sending this raw data. What is the distance for each pixel from the Kinect? What you can do with that information is incredibly powerful. And if we looked at any demo of the version 2 Kinect or the old Kinect, you would see it can recognize the form of my body very quickly and track where my arms are, my hand is, my head is, my knees are, and all sorts of stuff you can do with that. We don't have time, or I don't really to get into all of that here, and perhaps someday there'll be more videos or more examples that I can do and help prepare in that direction. However, I just want to jump back for a second and just show you what you can at least do, something that the Kinect makes possible with even just the raw depth information. So one thing I want to do is do this. Okay, so one thing you can see here is this is where I'm standing. As I walk closer to the Kinect, I start to turn red. As I walk further away, I stop being red. As I put my hand here, my hand is red. So with depth, one thing that you could do rather easily is say, where is the thing that's closest to the camera? And in the sense of a hand pointing straight out, that's pretty easy to track. Now notice I've put my other hand out. Now that dot is in between them. Take this one away, switch. So this isn't doing any sophisticated hand tracking. I could put my head here. It's just looking for a blob of stuff that's close to the camera. I could take this marker and point it out like this. And you can see it's sort of tracking that. I think this marker is actually a little bit reflective. So there's a lot more to this and how it works, and infrared light, and the depth versus the skeleton, and blah, blah, blah. And I'm just kind of doing a terrible job here. But what hopefully you got a sense in this video, if you're still watching, is that for loop, right, of looking through all the pixels, you need that. You need that for the image processing stuff you're doing. You need that for some computer vision stuff. And in fact, you need it for this. Because instead of looking for the color that's the most closest to whatever, I'm looking for the pixel that's the closest to the Kinect itself. So that for loop is pretty crucial. And there's a lot of things you can do with computer vision. However, there are also, you could do from scratch on your own, but there are also a tremendous set of libraries and resources and other devices like a depth sensor that you might consider as well. Very last thing is I'll try to include a link also. There are third-party applications, open source ones, like Community Core Vision, OpenTSPS. These are applications that you can run behind the scenes on your computer and have them pass messages about what they're tracking to processing. And that's also a way that you might think about in developing computer vision, an application that involves computer vision. Okay, so someday I will kind of revisit some of this stuff in a hopefully more organized or useful way. But for now, I'm just going to say goodbye, and I have no idea. This is probably way too long. Okay, but I did manage to get the Kinect working in this video, which is kind of interesting. Okay.